Good morning. Today we're going to talk about Chapter 5, Discrete Probability Distributions, and in particular Section 5.2. And Section 5.2 is entitled Probability Distributions. Alright, first I want to define a random variable. A random variable, well, the first thing it is a variable, just like x, y, z in a first algebra course. A random variable is first and foremost a variable whose values are determined by chance, a probability type experiment. I'm going to define a random variable here. Let x equal the number of heads in 3 flips of a fair coin. Alright, as we know, if you're talking about 3 flips of a fair coin, well, I've got 3 trials with 2 outcomes per trial, 2 times 2 times 2, so I'm going to get a total of 8 outcomes, allowing any coin to be of any flip and in any order. Alright, the possible values for x I'm going to list here in a table. X could be 0 heads, 1 head, 2 heads, or 3 heads. And each of these values of x will occur with different probabilities. Well, if you're talking about number of heads, I claim there's only 1 outcome out of 8 that has 0 heads. That's tail, tail, tail. Similarly, there is only 1 outcome out of these 8 that has 3 heads. That's heads, heads, heads. Now if you're talking about 1 head, well, 1 head means 1 head and 2 tails, and there are 3 slots available for that 1 head. Similarly, there would be 3 slots available for 1 tail if you're looking for 2 heads. So this is my probability distribution for x. And what a probability distribution does, it distributes 1 unit of probability amongst all possible values of a random variable. You can convince yourself of that by noting the p of x column adds up to 1, and that always happens in a probability distribution. Now, let me write this down. A probability distribution, I will say this, distributes 1 unit of probability among all possible values of a random variable. Okay? Alright, so that's our first example of a probability distribution. Let's talk about a mean of a random variable. What does it mean to find the mean of a random variable? Well, this is different from data. We're talking about a random variable whose probability distribution is given typically in theoretical terms. Well, this mean of a random variable, we grind it out like so. We take each x value, weight it or multiply it by its associated probability, and add up those products. Let's do an example. For x equal the number of heads in 3 flips. Well, let me copy down that previously computed probability distribution. Well, p of x was 1/8, 3/8, 3/8, and 1/8. So if I want to find the mean, I take each x and multiply it by its associated probability and then add up those products. Well, I'll get 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. And if I multiply these and add them together, let's see, I'll get a 0. I'll get 3/8 plus 6/8 plus 3/8. Let me write that down. 3/8 plus 6/8 plus 3/8. I'll get 6, 7, 8, 9, 10, 11, 12 equals 12/8. And if I decimalize that, of course, I get a 1.5. So for this random variable x, I claim the mean value is 1.5. Okay, so that's how we compute mean of a random variable. Let's consider a standard deviation of a random variable. Well, this one's a little harder. We give it the symbol sigma, lowercase Greek letter sigma, and I compute it in this fashion. Now, the formula should look somewhat familiar to the formula for a standard deviation from raw data. Right? We take each x value, square it first, then multiply it by its associated probability, add up those products, and subtract your previously computed mean, and then take the square root of the entire mess before, right? Let me briefly copy down this probability distribution again for the 3 number of heads in 3 flips. Well, again, what I want to do is I'm going to create a third column in this probability distribution and call it x squared times p of x. Alright, well, let me fill in these probabilities first. 1/8, 3/8, 3/8, and 1/8, right? Alright, so I'm interested in the sum of this third column here, which I will label x squared times p of x. And I take each of these values of x, square them first, and then multiply it by the associated probability. Alright, so 0 squared is 0, and 0 times 1/8 is, I'll just put in 0 times 1/8 for now, okay? Similarly, 1 squared is 1, and 1 times 3/8 is going to be 3/8. 2 squared is 4. So here I'll get 4 times 3/8, and 3 squared is 9, and I'll get 9 times 1/8. Okay? Alright. I'm going to now say the summation of x squared times p of x. Really, the summation of this third column is going to be, well, 0 times 1/8 is 0, plus 1 times 3/8 is 3/8, plus 4 times 3/8, that's going to be 12/8, and I'll leave it unsimplified for a moment, and 9 times 1/8 is 9/8. So I'll add these products together now. I'll get 3/8 plus 12/8 is 15/8, plus 9 is 24/8, and 24/8 is, of course, 3. So this value here now is going to be this part of my radicand in the standard deviation formula. So sigma, the standard deviation, is going to be 3 minus my previously computed mean was 1.5 squared. 3 minus 1.5 squared, and the square root of that difference. Let me get my calculator here. So 3 minus 1.5 squared be 0.75, and the square root of 0.75 is going to be 0.867. I'll call it 0.87. So the standard deviation for my random variable x was found to be 0.87. Alright, let me summarize that in a little bit of a summary here. Let's say, so, for x equal the number of heads in 3 flips of a fair coin, the mean was 1.5 and the standard deviation was 0.87. Okay? Alright. Please note, if I'm talking about mu equals the mean of a random variable, well, this is really a theoretical concept based on theoretical probabilities. What I'm really describing here is a theoretical mean outcome for infinitely many trials of an experiment. Hence, we also refer to this mean value as cap E, where cap E is expected value. So these symbols, E and mu, can be thrown around interchangeably, and they both mean the same thing, summation x times p of x. And you'll see the book invoking one of these symbols or the other interchangeably. Let's do another example. I'm going to let x equal the number of girls in 2 births. A little bit of a simpler example. Well, in 2 births, of course, we know we have 4 outcomes. 2 genders per trial. So 2 times 2 is going to be 4 possible outcomes. Now, we can't always draw the sample space. Sometimes it's too cumbersome. But certainly I can draw it here without too much effort. Let x equal the number of girls in 2 births. I'll say find the mean and standard deviation for x in this simple case. Alright, first thing I'll need to do is construct the probability distribution. If I'm talking about number of girls in 2 births, I could have 0 girls, or 1 girl, or a maximum of 2 girls. Well, how many of these outcomes correspond to 0 girls? Well, that's 1. There's 1 out of 4 outcomes that is 0 girls. I'll decimalize it here, 0.25. Similarly, the probability of 2 girls in 2 births, that's 1 out of 4 outcomes, and that's 0.25. And the probability then of 1 girl, well, notice, because I know the sum of the probability column has to be 1, there's only 1 cell left, and so this has to be a 0.5. If you want to look at the sample space, well, 2 of those outcomes have 1 girl, boy girl, or girl boy. And so I can say 2 out of 4 is also 1/2. Alright, so I can find the probability distribution without too much trouble. Now I'm going to find the mean. The mean equals the expected value, which is summation x times p of x. Alright, so I'll take each x value, multiply it by its associated probability. X equals 1 with 0.5 probability, plus x equals 2 with 0.25 probability. And if I multiply all this out and add up, well, 0 times anything is 0, 1 times 1/2 is 1/2, and 2 times 1/4 is 1/2, and those add up to 1. So the mean for this random variable is 1. Let me write that down up here. The mean is 1, because now I'm going to use the space to compute the standard deviation. And that's a little harder. Alright, the standard deviation. Well, the formula for standard deviation is sigma equals square root of summation x squared times p of x minus mu squared. Mu we already have. Well, we need an x squared times p of x column as before, and then the sum of that column is going to be this term under the radical sign. Alright, x squared times p of x. Well, 0 squared is 0 times anything is 0. So that was easy. 1 squared is 1. 1 times a half is a half. 2 squared is 4. 4 times a quarter is 1. So I can see then that the sum of this x squared times p of x column has got to be 1.5 or 1.5. And this is what we will sub in for this term under the radical sign. So sigma equals square root of 1.5 minus the previously computed mean was 1. So 1 minus 1 squared. Sigma then equals 1.5 minus 1 is 0.5 under the square root sign, of course, and the square root of 0.5 is 0.707. So I saw for this random variable x, the mean was 1, and the standard deviation was 0.707. Fresh screen here. Alright. Example. Let's play the New York State daily number. And I will expose to you here the folly of playing games of chance. The rules of the game are somewhat simplified here. I'll say we pay $1 and we pick a 3-digit number. If we hit, we win this game. The same number comes up in the random choice, each digit correct in the proper order. Let's say we win $500. I'm going to define a random variable under this scenario. I'm going to let x equal your net winnings in dollars. In playing this game. And I'll say find the expected value for x. Alright, if you're playing the New York State daily number, well, there's two outcomes essentially. You either win or you lose. Now you win or you lose, of course, with different payouts. If you lose this game, well, you're out the dollar. So my net winnings in that case would be a -1. If I win this game, well, remember x is net winnings, so I take my $500, subtract off the dollar I spent, and I've got a net gain of $4.99. So two possible outcomes with x taking on these two possible corresponding values, and they both occur with different probability. If I lose this game, well, I claim there's 1,000 3-digit numbers, right? From 000 to 999, and all but one of them is a loser. So I claim you lose $1 with probability 999 divided by 1,000. Similarly, only 1 out of 1,000 possible 3-digit numbers wins, so that means the probability of winning this game is 1 over 1,000. So my expected value for x, remember the expected value is the mean, and all it is summation x times p of x. I take each x value, weight it or multiply it by its associated probability, and add up those products. So I'll get minus 999 over 1,000 plus 499 over 1,000 and end up with minus 500 over 1,000, which gives me an expected value finally of negative 0.5. And since x is in dollars, my expected value for x is in dollars. Alright, and I think you can appreciate this negative sign is not here by accident. This represents the edge of the house. Really what I'm saying here is if you play this game an infinite number of times, you will lose 50 cents each time you play. And again, this is theoretically and on average. So let me write that down. This represents a theoretical mean value for x, your net winnings, for infinitely many plays of the game. And of course, all games of chance are set up in this fashion. They're all set up so that your expectation as a player is negative, and of course that value represents the house's edge. Remember the gambler's adage, the house never loses. Let's talk about usual and unusual values for a random variable. Well, similar to the boundaries we've seen before for raw data, if you are within 2 standard deviations of your mean, we call those usual random variable values, and anything beyond that we will label somewhat arbitrarily as unusual. Alright, so in our homework problems, when they ask us our values are usual or not, basically you've got to plot them in this scenario. Let's do an example. I'm going to let x equal the number of games played in a World Series. As some of us know, a World Series can happen with a minimum of 4 games and a maximum of 7 games. You can play as few as 4 and as many as 7, right? Now looking at past history, we can see the probabilities of each of these cases. Well, the probability that a World Series lasted 4 games was 0.19. The probability that a World Series lasted 5 games was 0.22, etc. Alright, what I'm going to ask us to do here is find the mean and standard deviation for this random variable x as defined. Well, of course, the mean is the expected value also, and that's summation x times p of x. And I can punch that out. It's 4 times 0.19 plus 5 times 0.22 plus 6 times 0.23 plus 7 times 0.36. And let me get my calculator out. Give me a minute here. 4 times 0.19 plus 5 times 0.22 plus 6 times 0.23 plus 7 times 0.36. And I get an expected value, a mean value of 5.76. Mu equals 5.76 for this random variable. Alright, let me put that up here. Mu equals 5.76 because of course we're going to need it to compute our standard deviation. Let me erase this now. Now I want the standard deviation. Of course, we remember our formula for standard deviation. Square root of summation x squared times p of x minus the square of mu. Again, I'm going to make a third column here. I'll call it x squared times p of x. And let me grind this out with you. Remember to square first your x value, then multiply by the probability. 4 squared is 16. 16 times 0.19 gives me 3.04. Alright, 5 squared is 25 times 0.22. Watch me here, it's 5.5, right? 6 squared is 36 times its associated probability, 0.23. I get 8.28. 7 squared is 49. 49 times its associated probability is 0.36. I get 17.64. So again, the sum of this column is summation x squared times p of x. I get 17.64 plus 8.28 plus 5.5 plus 3.04 equals 34.46. Alright, so this value gets substituted right here in my standard deviation formula. Standard deviation then is 34.46 minus the previously computed mean was 5.76 squared. Don't forget to square it. Easy step to forget. So if I punch this out, 34.46 minus 5.76 squared equals, and I have to take the square root of all that, I get finally a standard deviation of 1.13. Alright, so if x is the number of games in a World Series, I claim the mean number of World Series for the number of games, is 5.76, right? 5.76, and the standard deviation was 1.13. Okay? Alright, now I want to pose the question about usual or unusual values. Let me pose this question. Is it unusual for a team to sweep the World Series? Now, of course, a sweep means to win the first 4 games. And let's see, that does happen sometimes. Let's see if it's unusual based on our criteria given above. I'm going to set my boundaries for usualness as so. Anything within these boundaries, mu minus 2 theta to mu plus 2, or mu minus 2 sigma to mu plus 2 sigma, we will call usual. And anything beyond, unusual. Alright, well, mu plus 2 sigma. Here that's going to be 5.76 plus 2 times 1.13. And I get 8.02 as an upper limit here. Mu minus 2 sigma is going to be 5.76 minus 2 times 1.13, and that grinds out as a 3.5. So according to these criteria, if you've got a sweep, that means the World Series lasted 4 games, and if x equals 4, that clearly, according to this criteria, is not unusual. Okay? Alright, this concludes our section 5.2 probability distributions, and that's it.